Okay, good morning friends. Now, let us start today's lecture. I think we have missed quite a bit in between. I think we are meeting after about 2 weeks, if it is not more. It's almost 2 weeks that we are. I think one week was this mid semester break and another week was forced by me, I mean, on you. So, okay, if I remember right, I think I was trying to derive the finite element equations using energy principle, energy principle for one dimensional element. And then I told you that there is a very significant energy principle that is called principle of minimum potential energy that comes handy in deriving the equilibrium equations, the discrete equilibrium equations, because we are deriving the discrete equilibrium equation, of an element. So, it comes very handy to derive this equation indirectly. That means, we are not deriving the equations by showing the forces on the element as we had done originally when we started the course. This is an indirect way of deriving equilibrium equations, because after all, when the body is in a state of equilibrium, the energy, the potential energy has to be minimum. So, we minimize the energy. Okay. So, by minimizing the energy, we say that whatever conditions we get, that is our condition of equilibrium. Of course, I had explained to you the 3 types of equilibrium states that exist. We are interested in stable equilibrium. But since most of the structures, most of the systems that we deal with are in a state of equilibrium in a stable condition, so we do not go to the second derivative to checking whether energy is positive, change in energy is positive or negative, because otherwise you have to check whether it is in neutral equilibrium or unstable equilibrium or stable equilibrium. So, we assume that yes, body is in a state of stable equilibrium, and the condition that is there, first condition is that energy must be minimum. And I think I had come up to the what was that? Constitutive relations, if I remember. Now, today see that one, now you please it can be completed without any difficulty. I think we will take it up. Now, today I will give you a general description for any general body. Let us, because that will become a subset, that will become a special case of whatever I will talk to you later. So, there is any general body, elastic, the body is in a state of, this is subjected to loads and it is properly supported. Etc. So, there are number of, and it is and if you say that, so any point over here in this inside body, this is a 3-dimensional body. So, we are now saying how to derive. Today what we will do, directly we are jumping over to 3-dimensional body, because then we can derive all others as a special cases. Of course, I will complete that also little later, but let me complete this, because at least you will have a feel for a general description. So, at any point you have the point P will undergo a displacement u and u is ui plus v j plus w k, where u v w, that means u v w any point will have 3 displacement component 3. Okay. So, so first one is first. So, you have displacement. So, first thing is in finite element analysis, as we have been seeing, is define your displacement field. How does displacement vary within the body? Of course, body is too big. So, we say how does displacement vary within a small element that we take out of that body. So, this V we will say okay, the best thing is we will make a small tetrahedron or some element around this, because a 3-dimensional body, the simplest element that you can think of is with 4 faces. This is a solid. This can be fitted, you cannot have 4 noded, yes, 4 noded to 4, yes, brick. A brick can be but it is not 4 noded. Brick looks like this. You know, brick element is the simplest. People, any solid can be filled up with a brick element like this, but brick element has got 8 nodes, but this one will have only 4 nodes, 3 at the base, 1 at the top. So, you join, there are 4 faces. So, these are the types of element. There can be several ways of filling the solid. So, basically you have u v w. So, your u can be approximated, because everything is approximation in FEM, the displacement u. This u means this scalar, now I am telling, u can be approximated to u hat. Let us say it is, and then u hat we write u hat as equal to, okay, let me write down this displacement which is a function of x, y, z within the element in terms of nodal values, in terms of, that means u of this, u of this, u of this and u of this. So, we write this as sigma n I. Now, here the shape function will be function of 3 dimension, because it is varying in, you know, we have to have a shape function that is a function of into u I going from 1 to n. In this case, n can be 4 or 8 depending upon the type of solid, type of element that you choose. Is it clear? So, similarly, we can also have V, but what you must realize is we are approximating the u displacement within the element in terms of only 4 nodal values or 3 nodal values or 8 nodal values. Actually, n should be infinite. So, therefore, it is approximate. So, this whenever you write, I mean you must, this is called discretization error. There is always a difference between u hat approximate and u. This is error. At any point, the exact value of u and the u hat that you are discretizing, you know, this process is called discretization. Why it is called discretization? Because these are discrete values. These are nodal values. Nodal values are fixed point values. So, discrete values. So, this process, this statement is discretization. So, the discrete value of u at any point minus the exact value. So, this is approximate and this one is exact. We always define our error as, so there is always a error involved and this is called discretization error. So, this is called So, this always exists in finite element. So, don't think of this method as panacea for getting exact solution for any given problem. No, it never gives you exact solution. It all depends upon your discretization. Yes, it gives you reasonably good solution, engineering solution for practical application. But if you say no, just like yesterday we solved that plate problem, I told you the analytical solution is exact solution of the Kirchhoff plate equation. Now, it so happens plate equation itself is approximate of 3 dimensional, but as far as that equation is concerned, you are solving, analytical solution is exact. There is no error there, but you will never get here exact. You will always get some approximate solution. Okay. So, whenever you solve, so this discretization error is always there. So, now we can, so having given this, so now we can, our standard procedure is first discretize the displacement. So, we write u equal to ni ui. Now, ni means nodal values. I am not writing x y z, it is implied that it is a function of x y z. V equal to, now v means I am now writing, it is not equal to, actually it is approximately everywhere. If I write u and v, then it must be approximate, sigma ni vi, w equal to ni wi. Now, all these can be written. So, this is initial way of writing ni vi and summation over number of nodes. We can put this in matrix form, u v w and there will be a big matrix here, and I want to put them like this. So, this is, so I will write, I want to write like u1 v1 node wise, u2 v2 w2. So, it all depends upon you how you want to write down. Then un Vn Wn. So, if you want to arrange all your nodal values, because here it is general, in the previous one I had written in initial notation, yes, this is going from I is going from 1 to n number of nodes. Is it okay? So, I can express this now, I can write this also 1 to n. Now, I want to write this in matrix form. So, first one is n1 u1. So, what will be there? I will get here n1, is it n1 should be here, shape function n1 should be here, n1 u1. Next one here should be 0. So, first block should be 0 like this. Now, v equal to this 0 into u1, because I do not want anything from. So, here 0, then here n1, then here 0. W should be W third row, this into this. So, it will be, next block will be n2. Please see, it all depends upon how you arrange your nodal displacement vector here. Some people like to call it u1, u2, u3 here. I mean, like u1, u2 and then all u's first, then all v's second, then w, but then this is nodal wise is a better way of writing. So, this one will be So, like this there will be number of, and lastly it will be n nn 0 0 0 nn 0 0 0. Is it okay or I have made a mistake? Because then I will get u equal to u1, then u2, yes, then this is okay. So, the first relationship, so you can write this in matrix form also, and therefore, everywhere I am writing equal to, but please note these are all approximation. There is no, if you write this must be, and therefore, u v w u. So, therefore, if you call this as a vector, u v w consists of a u vector. U vector, if you do not buy a bold face letter in a books, you can write this in a bold face, but we will write like this with a curl. And then this matrix is our shape function matrix n, and this is nodal displacement vector. Is it okay or not? Because these are all the, we have put all the displacement of the node. So, that one you denote by D. So, this is a rectangular matrix, that is why there is a horizontal, there is a this is a rectangular matrix, this is a vertical matrix, or we call it also vector, this is also a vertical. So, this is, for example, this is 3 by 1, this is 3 by 3 rows, but how many columns? N into 3 n. Each node has got 3 degrees of freedom. So, it is 3 by 3 n, and then this one is 3 n, because this is n and 3 times, because u v w for every node 3 degrees of freedom. So, if there are n nodes, so this will most general case, this will be 3 n by 1 size of this. So, this must be kept in mind. So, this is, so you have established the I mean shape function can be derived, we have established. So, this is always the first step for any elastic. This we have done also for our one dimensional rod that I had taken, axial bar I had taken last time. This we have established actually, that is 1 minus x by L and x by L, n1 n2, because it was only 2 noded. So, there was shape functions of the 2 noded linear element was 1 minus x by L and x by L. But here for a general, so it is a very simple thing, it looks only complicated, tedious, but it is not so, but you just learn. Yes. So, having established the displacement, once you get this displacement, next part is always, yes, once you have defined your displacement, yes, for any elastic, you must define your strains. So, first part is always displacement, second part I think this I have been specifying also, strains in the body. What are the strains caused in the body because of the displacement field? So, now strains for a 3-dimensional body. In a 3-dimensional body there is some relationship between displacement, continuum displacement and strains. For example, epsilon x, there are 3, first of all there are how many strains? 6, yes. So, you have this is equal to du by dx, strain at any point is given by this. So, again for any problem, so this is the good thing about finite element is that anybody who has some knowledge, some intelligence, who has learned one area of theory, that means he may be a person not knowing solid mechanics, he would have done, let us say, heat transfer. But if he wants to change over to solid mechanics or formulate a problem, it is possible, because the steps are all standard. So, you find out the strains, now then the shear strains. So, in plane shear strains, So, these are the continuum relations which relate the 3 displacement u v w to the 6 components of strain that occur at any point, 3 linear strains and 3 shear strains. So, next we write this in matrix notation, total thing. So, this can be written in matrix notation. So, this matrix notation, we define all the 6 components of a strain by a strain vector, just like there I have defined by a u vector u. U can consist of any number of component. Of course, you cannot have more than 3. In a 3 dimensional, you cannot have 4 dimensional body or 6 dimensional. So, maximum is 3 dimensional body. So, 3 components u. So, here strains. So, we define this strain by a strain vector. So, strain is like this. This is not a tensorial strain vector. It is a engineering strain vector, because I have used here gamma. If you want tensorial strain vector, then I have to use half. I have to use here epsilon x y, epsilon x z, and then write here half, because half makes it tensor. So, this one is epsilon x, epsilon y, epsilon z, gamma x y, gamma x z, and gamma y z. And this can be, we can write this in matrix notation. Of course, it has to have 6 rows. So, 6 rows, and how many columns, please? Right hand side only u v w are there. This. Now, I have to fill up. So, for example, du by dx, del by del x u, first into u. So, del by del x into u is du by dx, next one has to be 0, next one has to be 0. Second one, so it is only a filling up, Initially, when I learned finite element, what is this? There is no mechanics. It is only filling the numbers in matrix, rectangular. So, this is what, but that is how we create all these matrices. We have to create these matrices, because matrix is the language of computer. So, this is this z, then here x y del u by, so this is del by del y, and then v by x, del by del x, this will be 0. Then here del u by del z, it all depends upon, do not take it blindly, you see how it is written and how people are following. So, different books will give you different, and there is no w. So, here it is 0 and del by del x, and last one del v by del z. So, this one x is not there, u is not there. So, this will be 0 del v by del z and del w by del y. Okay. So, the same 6 relations are written in a matrix notation now. Is it okay? 6 by, so this is 6 by 1, this is 6 by 3, and this one is 3 by 1. So, finally, it is 6 by 1 both sides. Now, this matrix which consists of only derivatives, in general derivatives means only there is nothing, just it is called del by del x, del by del y, only derivatives, we call it by derivative matrix, and we denote it by a letter. So, this one will denote, see left hand side is epsilon. So, I will just try to compress it here, left hand side is epsilon. By the way, even a strain, this is up to here it is exact, there is no whatever you have written, all these relations are exact, elasticity relation. But the moment, yes, up to here also this will be exact. I think we have not yet introduced discretization. So, here, so this is everything is exact here. This matrix, this 6 by 3 matrix will denote by a letter L, a symbol L. It is a rectangular matrix 6 by 3, and this one we are denoting by what? U. UVW we have been denoting by U. So, we got another relation. So, this is again, see, please remember these. Actually, whenever you are solving any elastic problem, and this is how finite element method got developed. These are basic relations. We have to establish these matrices. Similarly, the first one was this. You have to establish this. So, this is an important block. N has to be established. Now, L you got it. So, now you have got L, derivative matrix, yes, we have put it, this is in place, derivative matrix, and this is, but then just now, but I would like to know what is my strain in terms of my nodal values. This is the continuum displacement, UVW of any displacement of any point P, but I do not want any point P. My element is there is a point P. I want the all my formulation in terms of discrete values. So, I have got a relation. So, this is equal to, so now it is all standard. So, strain, therefore, next one strain. Now, it is equal to, here it is equal to, please note here this one is equal to. I want to substitute for U equal to N into D, but since this is approximate, now my strain will become approximate. So, this is equal to L times U, and U equal to N times D, N times D. N is the shape function matrix, D is the nodal displacement vector. So, now strain at any point within the element or within the body in terms of nodal values that you have chosen, nodal values vector is this, is given by L times. And then this matrix, I think if you just compare this with our one dimensional formulation, which I think they have explicitly defined what is this one dimensional, I think I had done 1D rod for the rod, how this is coming. Because there it is simple one single relation. So, this matrix, the matrix that converts the nodal displacement to strain at any point is called strain matrix. So, this matrix is strain matrix, and we denote it by a symbol B. I think there also I had shown it B. How many people remember? Did I tell B in the case of one dimensional? So, this is a strain matrix. So, we denoted this one as L into this equal to, that means this equal to B times D, and B is equal to L into N. So, you have to multiply two matrices. So, what is B matrix? B matrix, what is L? L matrix is 6 by 3. 6 by 3, just now we saw del by del x 0, 0, and N is a big matrix, etc. This del by del y 0, this del by del z 0, del by del y, del by del x 0, del by del z, and del by del x, then 0, del by del z, del by del y. So, this is your L and N matrix is this matrix, you see N. N is quite a big matrix. This is my N. So, if you, what will be the multiply? You have to multiply this. So, you have to multiply this, multiplied by 3 by that N, N1 0 0 0 N1 0 0 0 N1 etc. going like this to Nn 0 0 0 Nn 0 0 0 Nn. It is like this. So, you do not think only 2, I have written only 2 blocks, there are number of blocks in between, block of 3 by 3, these are all block of 3 by 3. So, this one will be 6 by, by the way this is B matrix. So, B matrix L into N. So, this one will be 6 by 3 and this is 3 by how many? 3 N, 3 by 3 N, there are 3 N columns. So, total thing will be 6 by 3 N, 6 by 3 N, it is quite a big. So, in olden days we used to take a big sheet of paper and write 6 by to understand, but these days you do not, because we know I going from 1 to N, something like that, we can always do. So, I will write. So, this is, but then this is how it is done, because you can understand this only. So, B matrix is, so what is your B matrix? Continued B matrix. So, how will it look like? B matrix will look like, it is 6 by, so yes, if you multiply this, so it will be N1. So, first block will be dN1 0 0, sorry dN1 by dx. Second block, everywhere dN1 by dy 0. Third block, sorry third row dN1 by dz. Then the next one w, uv third row N1. What will be this? This is okay or I made a mistake? If you multiply these two matrices, please, what will I get? This is okay. N1 only, na? Because this row, this column N1, this row, this column, second row, third column. Now, this row, this column. So, it will be this column. This row, this column. Is it correct or not? Yes. So, we will get a 0. dN1 by dy, that is all. What about this? This multiplied by 0, this second one is coming 0. I am little, I think we have not made any mistake. Okay, so this row, so then third one will be this one, this into this d dy. This is interesting. Then this row. No, I think I am making a mistake. You see, this is the fourth, na? Fourth row has to be 2 elements. That is why I am saying, Yes, DNN, that is what I was, because I am checking with you people. So, you said, this is right, but it should be dN1 by dx should be there here. But how it is coming? This row multiplied by which one? Which column? Huh?
So, fourth row first column is giving dN1 by dy, fourth row second column will give dN1 by dx.
This is fourth. Fourth is here. Fourth is here. So, how do you do multiplication? Huh? I know that. I mean, that is why I was. This has to be like this, but still I am not very happy. I am not getting. This one will be dN1 by dz, 0 dN1 by dx, and then this one will be 0 dN1 by dz, dN1 by dy, and similarly for the second one will be, now this is all first block is only N1, second block will be similarly with all N2. And like this number of blocks, and B matrix is quite a big one. So, last one will be here n. So, d n n by dx 0 0, and then this is then 0 d n n by dy 0 0 0 d n n by dz, and then d 3 are over, fourth one d n n by dy d n n. I will ask you later how did you get this. And d n n by dz. Sorry, see, last one is 0 here. There is a 0 here. There is a 0 here, and then d n n by dz and d n n by dy. It looks like, is it okay? Multiplication is all right, but I am not clear. I have forgotten my matrix multiplication. So, anyway, I will not spend time on multiplication. So, so this is okay. So, it looks nice, this is the derivative. So, B is a derivative of shape function matrix. I think this I have been emphasizing even earlier for one dimensional. So, it is basically it is a derivative. So, for any problem that you have so you just take resistance displacement relation and please derive your B matrix. So, B matrix is very important, N matrix is very important. Unless you have N matrix, you cannot derive B matrix. So, N and B now are derived. So, they have to be explicitly derived. Now, how do you do this? Now, this can be written now. See, now we have got, because after in the olden days we used to write this total thing in the computer. Now, I think we can generate this into computer, because each block you need to store only 6 by 3. I can write it by 6 by 3 here. you see here. So, B matrix can also be written as summation I going from 1 to n, and then this is it is not summation actually, it is not called summation, by the way, it is not summation, it is expansion. That means I know only one. So, therefore, what I will do here, I will write only B I. So, this one, yes, summation if I write, it will be a blunder, it is not a summation. So, this one I will express this here itself. I will write this block as B 1. This is also a matrix, it is a 6 by 3 matrix. This as B 2, then B 3, etc., going up to B n. Each one is a sub matrix, each one is a 3 by 6 matrix, sorry 6 by 3 matrix, each one is a 6 by 3 matrix, each B 1, B, this is a big matrix. So, now I can write here any general B I is any general ith, let us say ith for node I, it will be let us say B I. So, this one is 6 by 3, each one is 6 by 3. So, this one I can write. So, this one is, let us cancel this, no summation. I think let it be recorded that I made a mistake. So, this is not summation. So, I will write only B I is B I looks like just a general d n I by d x 0 0. So, it is okay. I think the rest of it you can fill up, 0 d n I 0 0 and similarly the other one d n I. Second one d n I by d z. d n I by d z, then x d n I by d x, and lastly d 0 d n I by d z and d n I by d y. So, I have defined a small sub matrix which is only a 6 by 3, and I can create all the rest my total B matrix. So, one is a simple matrix like this, and the total matrix looks like something like this. Okay? Is it okay? Have you understood? So, establish B matrix, a general B matrix. So, this we are talking of for any general elasticity. I think up to here I had completely done for one dimensional. All these matrices have been explicitly derived for one dimensional. So, okay, there is no difference. Now, let us, so B matrix has been derived, B strain matrix. Now, after strain matrix, of course, you should know your always at any point strains are produced because of displacements, and because of strains you will have stresses in the body will get stressed. So, there is a relationship that exists between stress and strain. So, that must be written for a given particular, that also it is always denoted by what, strain equal to strain in terms of stress can also be expressed, and stress in terms of strain can also be expressed. Now, it is easier to write the strains in terms of stresses. I think this I have been emphasizing everywhere. It is easier to write 3 dimensional, but the reverse form is a one that is used. So, we can write now what about the relationship, constitutive relationship between, that means stress strain Now, this is a physical relation. General. So, in a three dimensional body, let us say just for simplicity, it is a linear elastic. Body is linear elastic. Linear elastic means stress strain curve when you plot as load increases, it is linear. You are only referring to the linear portion, linear elastic and elastic. What is the meaning of elastic? When you unload, then it comes back to the same original position, body comes back to the original position. And isotropic, yes, there is only one. Somebody recently, I was in an interview and then I asked how do you define a isotropic body or isotropic material? Quite a middle level person, he said E, nu and G. For 5 minutes I said all these three are, there is no relationship, you need three constants to define isotropic material. Yes sir, three, we need three. No, we do not need three, we need only two. So therefore, isotropic material only you need E and nu or E or G or G or nu, anything, any combination of E, nu and G. Only you need only two constants, either this or this or this, because this exists. For isotropic material, this exists, sorry, not this, this. This relation exists. This relation exists. So, we can write down and this relation is a point relation. See, stress strain relation, that means strain and stress relation is a point wise relation, point. It is not for a body. You are plotting or you are seeing the strain and stress at a point in the body, not for the entire body. Somebody asked, when I said yes, what is the strain? Yes, sir, the strain in this body is this. No, unless the strain is uniform, you cannot say strain in this body is this. Strain will vary in the body generally from point to point. So, it is a point wise relationship. So, never forget. So, the next thing comes whether the body is homogeneous or not. Homogeneity brings in whether this relationship can be independent of point. Homogeneity. If the body is homogeneous, then only, so homogeneity will make it for the entire, stress strain relation. The relationship will be the same for every point within the body then, if the body is homogeneous. Otherwise, no, if the body is inhomogeneous, changing from point to point, it is a different, then obviously it will be. So, this is, so we define this. So, I think you read something about our relationship for various types of three dimensional. So, three dimensional, how do you relate stress to strain? How many people know? How do you define stress strain relationship for a three dimensional? So, for example, 1 at any point you have, we saw that we have got 6 strains. So, strain for example, strain in x direction can be written as, and if you apply a sigma x in the body, so that will produce epsilon x in the body, but that will also produce a epsilon y and epsilon z, but they will be compressive. So, this one will produce, for example, if I put, so this one will be sigma x by E, but then it will also produce sigma y and that will be minus nu times sigma x by E, and it will also produce sigma z, epsilon z, and that will be nu times again sigma x by. Is it okay? If it is isotropic body, if the body is isotropic, then it will a single sigma x applied in one direction, a stress applied in x direction will produce 3 strains, 3 normal strains. Will it produce any shear strains? No. So, gamma x y by this will be 0, gamma x z produced by sigma x will be 0 and gamma y z produced by this one will be 0. But then at a point in the body, if it is a general state of stress, you do not apply or there is no only sigma x, you also have sigma y, you also have sigma z, you also have tau x y shear stress, you also have x z y. So, all the 6 components of stresses are there. But a normal stress produces only normal strains. So, you see normal strains I am saying, a normal stress produces. So, similarly, if you superimpose on this element sigma y. So, sigma y means again strain will be sigma y. So, sigma y means plus and now superimposing sigma y by E. But then this will also produce strain in x direction, that will be nu times this and then this will be nu times sigma y by E. Will it produce any shear strains? No. If it is isotropic material, no shear. So, this again will be here, because of sigma y there will not be any shear strains, Similarly, third one, if I now superimpose sigma z, that means apply a tensile stress sigma z, so that obviously will produce a tensile strain epsilon z. So, it will be sigma z by E, but that also is accompanied by a negative strain in y and x direction. So, negative strains will be minus nu times sigma z by E and minus nu sigma z by E. Again this will not produce any. So, we are doing only for a very simple material. So, we have applied all the 3 normal stresses at a, but then you do not have only 3 stresses, you have more than 3 stresses at a point. What are the other stresses? Shear stresses. So, shear stress is always applied in pair, always they should be pointing, there is always a right angle and then shear stress. So, shear stress is always like this. Any corner you have a shear stress like this or a shear stress, they should be diverging. They should be acting like this or this. So, they will change the shape of the body. Shear stress produce a change in the shape. So, kindly complete this relationship for the general, apply also the shear stresses and complete this. So, that will give us a strain expressed in terms of stresses for a general 3-dimensional body. And then we can establish our elasticity matrix for a general body. So, this I will take up tomorrow. Yes, tomorrow we are meeting at 4, but there is no lecture in the morning for finite element. Okay, okay, thank you.